Hello lovely grade 12s. This is the video titled Mathematical Induction Part 2. So please do not watch this video until you've watched the first Mathematical Induction video. I think that one will just be titled Mathematical Induction. But if you haven't watched the first video, please do not watch this because you will have no idea what's going on. So continuing from the previous video, we already introduced the whole process of mathematical induction. And we're going to continue with that process of mathematical induction using some more examples, first on sequences and series, and then I'm going to go into type 2, which is examples on divisibility. So let's get straight into it. Now, the last example we have on that sequences and series was asked in the IAB 2017. Now, this is very much a Josh method, meaning that up until 2017, they've always asked sum of a series. And then suddenly in 2017, they said in question 4, prove by mathematical induction that this is equal to that formula. Now, if you notice, you'll notice the pluses are absent. We are not going and saying that term plus that term plus that term. No, in fact, what we're doing here is we are multiplying. We're saying this term multiplied by that term multiplied by the next term is equal to that. So this one was quite a bit of a tricky one. But you'll see, once I follow the steps, you'll see the steps are actually very much the same. So that was the first part, that this is actually not a proper series because it's a multiplication sum. It's not adding terms, it's multiplying terms. And then the other thing that was a little bit strange is they said for all integer values of n, where n is greater than or equal to 2. So they've specified here that it will only start with n greater than or equal to 2. Now be very careful because a lot of people then assumed that on the left hand side I needed to use this term and that term. No, you will notice that in the formula says to create these terms that I'm multiplying, I'm using 1 minus 1 over n squared. And if I put 2 in there, the first term is going to be 1 minus 1 over 4 because if I square 2, it's this one. So let's start. We're going to start with for n equal to, now careful, not 1, but 2. Because they said the first term is where n is equal to 2. So on the left-hand side, that means we're going to use that 1 minus a quarter, because 1 minus a quarter is what happens when you put 2 into this one. And that is going to give me 3 over 4. And then on the right-hand side, I'm going to have 2 subbing into that formula, so 2 plus 1 over 2 times 2, which is equal to 3 over 4, so 3 quarters. Yay. So left-hand side equal to right-hand side. Therefore, true for the first term, but careful, the first term is where n is equal to 2. Good, so that's my first step. Now the second step, we say assume for n equal to k. And that one, all I do for this particular step, I go to this part and I substitute all my n's with k. That's all I do. So 1 minus a quarter times 1 minus 1 over 9, skip a few, times 1 minus 1 over k squared. So everywhere where there is an n, I now put a k, is equal to k plus 1 over 2k. So I'm assuming this is a true statement. And now using this statement, I now go to the next term. So for n equal to k plus 1, which is the 2 consecutive terms. Now what I need to do here, if you recall, is I now need to go and I need to use this particular formula to create that next term, that n equal to k plus 1. And I need to multiply by that next term on the left-hand side and also on the right-hand side. What I do not do in this step is substitute k plus 1 in there. That's not what I do. That's what I'm going to try and prove. So I start over here and I write this down first. So 1 minus a quarter times 1 minus 1 over 9. And guys, you can't skip this. You can't just immediately jump into the term, which is the k plus 1 term. You still have to write all of this down and then just multiply by the next term. Because the number of times I've had to mark papers where people just thought, oh, I can skip this. You cannot skip this. You have to carry this down in the next step. And I'm going to multiply by that k term over there, 1 minus 1 over k squared. And then I'm going to multiply by the next term, the k plus 1 term. And like I said, to create that k plus 1 term, I use this formula over there, that formula on the left-hand side. So that then means it's going to be equal to 1 minus 1 over, please put a bracket around this, k plus 1 squared. And that is supposed to now be equal to this one, so I carry that one directly down. And what I add, oh sorry, careful, not add, multiply. See how easy it is to get this wrong. So I'm running out of space, so I'm just going to go multiply by. I'm not really supposed to do this. This is horrible notation, but I'm really running out of space. So just, if you have space, please make sure you multiply this term next to that. So what I multiplied by on the left-hand side, I also have to multiply by on the right-hand side. Which is that next term. And now I'm not going to look at the left-hand side anymore. I'm going to look at the right-hand side. And you have to note that I know exactly what the answer should be. So I can go and I can do that little cheat again. And hopefully I will have enough space over here. I'm seriously hoping I will, but let's just create some space just in case. And I know my answer over here I can get by using this part of the formula. So I'm going to use this part of the formula. My answer is going to come from that, but I'm going to substitute the n with k plus 1 because I'm trying to prove that sum of k plus 1 terms. So let's put that over there. So that's going to be equal to k plus 1 plus 1 over 2 times k plus 1. So that's what I'm trying to prove. Okay, good. So let's get cracking. Now over here, like I said, we need to go and simplify. So in order to simplify, yeah, this is not going to be very nice just because of these fractions. So I might actually need more space. Let's hope I have enough space over here. So I've got that k plus 1 that I'm multiplying over there, over 2k, where there's not much simplification to be done there. In this particular one, I need to get that LCM of the denominator, which is then going to be k plus 1 squared. Great. So over there, I need to multiply by k plus 1 squared minus 1. There we go. And now I can kind of look at where I'm headed, which is I'm headed over here. And if I'm headed over here, you should notice that, these denominators don't seem to be working very well. So maybe what we shouldn't do is we shouldn't really multiply these until I've simplified that top one over there. Until I've simplified it, let's see if maybe I cannot get something that will divide away, potentially. Well, technically speaking, hey, look at that. I didn't even spot it. I think Jared must have been going, ma'am, ma'am, ma'am. There it is. I can already divide away. Do you see that k plus 1 over here in the numerator? I've got a k plus 1 over there in the denominator. Oh, that's awesome. So I can actually, in the next step, I can say k plus 1 over here divides into that k plus 1 squared. So let's just write that down because that is much simpler to do. Please, people, whenever you do these ones, try go for the simplest option. So I've got k plus 1 over here. Then up top over here, if you look at that, we've got k plus 1 squared minus 1. Now if you look at k plus 1 squared minus 1, it doesn't look the same as where I'm headed. So I am going to expand this one now. And I'm going to say this is then equal to k squared plus 2k plus 1, and then that minus 1 carries down. Great. So in my next step, I'm going to multiply the two denominators by each other. So I've got the 2k times k plus 1. Then over here, I'm going to just go and say simplified k squared plus 2k, and then plus 1 minus 1 is going to eliminate. And I'm going to take out k as a common factor in those two terms that are left. Now you'll notice, look what happens over here. The k in the numerator divides into the k in the denominator, and then what do I have left? I have left k plus 2 over k times k plus 1. And this is exactly what I want because I've got, sorry, that was a mistake. I can hear Jared in my ears going, ma'am. Okay, let's just fix this. That's actually 2. Better. Okay, so over there, the k was what divided away. So I've got k plus 2 over there, and I've got the 2 times k plus 1. And if you look at it, k plus 2 can be split up into k plus 1. So check, this is mathematically equivalent to that. This is mathematically equivalent to that. So I've proven that simplified, it goes to this. So I find that this is normally the most difficult step in mathematical induction, because you know where you have to get, and sometimes your algebra is not always as good as it should be, or you can make silly mistakes that I made over there, where I forgot it, I didn't divide the 2 away, I divided the k away. But you know where you have to get to. So please, please, please just keep on going with those and try and make sure that you keep your mistakes to a minimum so you can get to that particular step. Now, almost done, because we need the conclusion. So the conclusion goes, therefore, by the process of mathematical induction, it is true for all integer values where n is greater than or equal to 2. And I had to write it out in a slightly longer way because the previous ones we started at 1, so you could just say it's true for all integer values, but this one is true for all integer values where n is greater than or equal to 2. Okay, so that was then the last example of this particular type. And like I said, this particular type is called sequences and series types. Now, the next type, and luckily these are the only 2 types that you have, is the divisibility of algebraic expressions type. So we're going to start this one by looking at the textbook, example 2 on page 13, where they say prove that the expression 9 to the power of n plus 3 is divisible by 4 for n an element of all the natural numbers. Now there are a couple of tricks here that you need to take very careful note of. So I am going to just, in this first one, I'm going to go and in the bubble again, which isn't part of the actual proof, but in the bubble I'm just going to remind you that if you don't do this, you're going to get stuck. Right. So it's the same process that we followed on the type 1, and we're going to start by saying for n equal to 1. Because remember, the natural numbers start at 1. So for n equal to 1. Now in this case, we don't have a left-hand side, right-hand side, because we're not trying to prove a series formula. So we're just going to use this particular formula, and we're going to say it's 9 to the power of 1 plus 3. So I'm substituting the 1 into that formula. And then I'm going to say this is equal to 9 plus 3, which is 12. And make this a habit. I know and you know that 12 is divisible by 4. But the habit is show that it's divisible by 4 by showing 3 times 4 is 12, which means if 4 is a factor of 12, and this is going to be important for the rest, if 4 is a factor of 12, then 12 is divisible by 4. So the moment you split it up like that, you can then just go and say, therefore, true for n equal to 1. So by writing that in factor format, showing 4 as the factor, it's divisible by 4, so it's true for n equal to 1. Now, assume for n equal to k. Now, again, this is different than the type 1, because now what we need to do is we need to say, if I take this expression again, and just as it is, I substitute k into it. Now I need to assume that this will be divisible by 4. And in order to assume that this is divisible by 4, I need to write it out like this. I need to say it's equal to 4 times r, where r is an element of the integers. Because any integer multiplied by 4 is going to have 4 as a factor, like I showed you over here. And because it has 4 as a factor, it is then divisible by 4. So in my assumption, I'm saying that this can be simplified in such a way that I will have 4 as a common factor. And because I have 4 as a common factor, it is therefore divisible by 4. So that part is brand new. You have to create that. And by the way, you have to also create this because we're going to use this as a substitution. Now, to prepare myself for the substitution, which happens in the next step, I'm quickly going to go and I'm going to say 9 to the power of k is equal to 4r minus 3. So this is just preparing the substitution. You'll see just now what I mean with preparing the substitution in the next step. So in a bubble, because it's not part of the actual sum, but it is important to remember this. And this, like I said, again, you have to memorize that, because if you don't memorize that, this is where your entire proof is going to fall completely flat, because you're going to forget about this and then you won't know how to go any further. So we're going to say for n equal to k plus 1. Now I'm just going to go and I'm going to substitute the k plus 1 into this expression, because I now want to prove that if I substitute k plus 1 into this expression, it's still going to be divisible by 4. So 4 will still be a common factor. So 9 to the power of k plus 1 plus 3. There we go. Now this again is something that if you don't remember it, you're going to get stuck. So I'm going to put it in the bubble there. You're always going to take whatever you substituted the k plus 1 into, you're going to go and split that. So you're going to go split the term, and you're going to do that by using that lovely little exponential law that says if I multiply two powers by each other and the bases are the same, then you can keep the base and you can add the exponents, except we don't use it going this way, we're going to use it going this way. So that means I can split this up into 9 to the power of k times 9 to the power of 1 plus 3. And this is what I meant with you need to prepare for the substitution. Because we now know that 9 to the power of k is 4r minus 3. So I can do the substitution over there, because this is also 9 to the power of k. And I can substitute 4r minus 3, and I'm just going to move 9 to the front to make it easier to do the distribution. There we go. And I'm going to multiply that in, so it's going to be 36r minus 27 plus 3, which is going to be equal to 36r minus 24. And then, like I explained to you guys up here, the moment 4 is a common factor, it's divisible by 4. So the only goal I have in this particular step is to finally get to an expression where I can take 4 out as a common factor, and specifically 4 because they asked prove that it's divisible by 4. Obviously, if they ask prove it's divisible by 8, you want to then show that 8 is a common factor over here. But the nice thing is, over here, if I look at that step, I can take 4 out as a common factor and left with 9r minus 6, which then means it is true. So therefore, true for n equal to k plus 1. So my conclusion, by process of mathematical induction, it is true for n as an element of the integers. And that's pretty much it. So we're going to do another one, and I'm going to speed it up slightly. So hopefully if I speed it up, you guys will be able to see it's really not as bad as you think. But I will refer back to the couple of tricks that I showed you. So question 3, and this was in the IB 2018 paper, use mathematical induction to prove that this expression, 2 to the power of 3n minus 3 to the power of n, is divisible by 5. So please remember, in this one, we need to get all of those common factors equal to 5, because we're not trying to prove divisibility by 4 like we did in the previous one. We're trying to prove divisibility by 5. So first step, for n equal to 1. And I just go and I use this expression and I substitute 1 in there. And I simplify. 2 to the power of 3 times 1, which is 2 to the power of 3, is 8. And 8 minus 3 is 5. And the nice thing is we're just going to write it as this is 1 times 5. Which means it's true for n equal to 1. Because 5 is a common factor, which means it's divisible by 5. Then assume for n equal to k, and I'm going to substitute k into this expression, so 2 to the power of 3k minus 3 to the power of k. And I need to show that this is equal to a factor of 5. Not a factor of 5, an expression that has got a common factor of 5. So I write that out as 5r, and again, that's where r is an element of the integers. We have to make this statement, because if r is not an element of the integers, this will not be, a multiple of 5. 5 will not then be a factor, and this will not be a multiple of 5. So I'm again going to go and I'm going to prep my substitution. So a lot of people then go like, well, should I prep it for this one or this one? It really doesn't matter. I always just stick to the first one. So I go 2 to the power of 3k is then equal to 5r plus 3 to the power of k. Good. Next step. For n equal to k plus 1. And I again go to this expression over there and I substitute k plus 1 in there. Now, I want to now go and I want to do the substitution. Before I do the substitution, I'm just going to go and expand that bracket. So I'm going to say it's 2 to the power of 3k plus 3 minus 3 to the power of k plus 1. And you don't really have to expand this one. This one, you can generally leave it like it is. So I'm going to break this up and I'm going to say it's 2 to the power of 3k times 2 to the power of 3 minus 3 to the power of k plus 1. And that's where I can now go and I can use my substitution to substitute that right there with that 5r plus 3k. Now again, I'm just going to take 2 to the power of 3, which is 8, and move it to the front. And then I'm going to substitute that with 5r plus 3 to the power of k. And you might want to go and now break this up, and you'll see just now why it's a good idea to break it up. So I'm going to break it up and say it's minus 3 to the power of k times 3 to the power of 1. Now when I do this distribution, I end up with 8 times 5, which is 40r, plus 8 times 3 to the power of k, which is 8 times 3 to the power of k, minus, and I'm going to move the 3 to the front. Because hopefully you guys will see these are like terms. 8 of those 3 to the power of k minus 3 of those 3 to the power of k. So that will then give me 8 of those minus 3 of those is going to be equal to 5 of those. And that's exactly what I'm striving for. I'm striving always in this last step to whatever I'm trying to prove divisible, in this case 5, to prove that 5 is a common factor. And what I can do now is I can take out 5, and then this will be 8r plus 3 to the power of k, which means therefore true for n equal to k plus 1. And by mathematical induction, it's true for n an element of all the natural numbers. So always remember your conclusion, because you always get marks for that conclusion. Right, one final example. I'm hoping after all of these examples you guys are starting to see the light at the end of the tunnel, and it is not a train waiting to run you over. But yeah, you're more than welcome to make comments on the Google Classroom and just say to me, please can you explain a couple of things on this. Okay. Now this last example is in the IB 2015 paper, question 2. Prove by mathematical induction that this expression 5 to the power of 2n minus 1 is divisible by 8 for every positive integer n. Okay, so we start again saying for n equal to 1, because obviously the positive integers start at 1. So positive integers start at 1. And I'm going to say it's 5 to the power of 2 times 1 minus 1. And this is going to be 5 squared, which is 25, and 25 minus 1 is going to be equal to 24. And I'm just going to write that out so that I have that common factor of 8, because then it's divisible by 8. So it's going to be 3 times 8. Therefore, it's true for n equal to 1. Great. Now we're going to just do the substitution of n equal to k, which means 5 to the power of 2k minus 1. And I now have to go and create that multiple of 8. So I need to say it's 8 times r, which is a multiple of 8, and the multiple of 8 is divisible by 8. So where r is an element of the integers. And I'm going to prep the substitution, saying 5 to the power of 2k is 8r plus 1. Now the last full step for n equal, actually I should have said assume, there we go, for n equal to k plus 1. We now again just go back to this formula and we substitute k plus 1 in there. And I'm going to just have to do some exponential simplification there. So I'm going to do it in 2 steps. I'm going to multiply the 2 in, but I'm also going to break it up. So I'm going to say it's 5 to the power of 2k times 5 to the power of 2 times 1, which is 2 minus 1. Okay, now here's my substitution again. So my substitution is going to be over there, and I'm going to substitute that 8r plus 1 into this. And that 5 squared is 25. I'm just going to move it to the front of the bracket. Then if I expand that, 25 times 8, that's going to be equal to, wow, 200 if I'm not mistaken. 200r plus 25 minus 1 is then equal to 200r plus 24. And again, what am I trying to prove? I'm trying to prove that it's divisible by 8. So I want to prove 8 is a common factor. So I just take 8 out as a common factor, and what I'm left with there is going to be 25r plus 3. So therefore, true for n equal to k plus 1. And then my conclusion is, by mathematical induction, true for every positive integer. So positive integers, if you really think about it, you can actually just go and say the natural numbers, because the positive integers are the natural numbers. So thank you for listening. Just last little comment on mathematical induction. There's always a mathematical induction question. They ask it in every single paper. They've never not asked it. And it's a very nice question in the sense that it's procedural. So you can see it follows quite nicely, and they normally give it like anything between 10 and 14 marks. So don't go and say, no, I don't want to do this. This is probably one of the easiest questions that you're going to get. And it's also a question you expect. So I sometimes find in the paper, if you're getting to one of these questions that you expect to find, then it actually calms you down, because you look at it, you go, I recognize this question. I know how to do this question. It's nice, easy marks to get. So thank you for listening.